Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Maia Williams and Simone Dichiara with us today. Hi, Maia. Hi, Simone.
Hi.
Hi.
Hi there. Well, thanks so much for being to talk about your very lovely article.
Thanks for having us.
Yeah, sure. And let's see. Maia, what's your geolocation? Where are you at?
I am in State College, Pennsylvania at Penn State.
Pennsylvania. Very cool. And Simone?
Me too, but I'm at home right now.
Okay, very good.
Working from here.
Yay. It is April 13th of 2023 as we record this, and is spring in the air in Pennsylvania? Do we have buds, flowers?
Summer is kind of in the air.
Summer. Okay.
It's
been
kicking
really
in,
warm
yeah.
this week.
Wow. Okay. Yeah, we are definitely I'm in Phoenix, and we are definitely in our early summer at this point. So the temperatures are getting over 90 these days. But it's a dry heat. It's a dry heat.
I think we should be back down to 50s, 60s by next week. So
Yeah, that's right.
Okay. We're doing the roller coaster kind of approach to spring or summer. Very cool. Nice. And Maia, what do you like to do for research?
Well, the past few months have been this GRB.
Yes.
And then before that,
oh, you remember what happened before this one? Oh, okay.
Yeah. Before that, I was doing some research with the X-ray binaries in the Small Magellanic Cloud.
Very cool. Very cool. Simone, what do you like to do?
My field of research is mainly focused on multi-messenger time domain astronomy. I'm basically focused on GRB and gravitational wave counterpart.
That's a combo.
Kind of stuff.
Very cool. Very cool. And that is going to bring us to this very lovely APJ letter. Two things on this. Number one, it's open access. You can go grab a copy, people. Go get one for free. And number two, this is a 24-page APJ letter, which goes to show that the primary metric for publishing in letters is impact. It's not length. Okay, length is a secondary concern on letters. GRB 2022-1009A, discovery of an exceptionally rare nearby and energetic gamma ray burst. And Maia and Simone, take us away.
Okay, well, first of all, I'd like to give a quick thank you to all of our authors. We have a lot of them. Just some few major people. Jamie Kenna is the lead of the Swift Science Operations team. Kohei Kobayashi and Hitoshi Nagoro are from the Maxi team. Wataru Irakiri is from the NICER team. Andy Beardmore, Phil Evans, Sebastian Hines all worked on XRT stuff and dust ring analysis. Amy Lian did the rate analysis and some of the BAT data. Sam Oates worked on the UVOT data. And Brad Senko is the Swift PI and helped a lot with writing. So, and all the people that I didn't mention from the Swift team, including the Swift Flight Operations team, and everyone from the Maxi and NICER team. This was a giant collaboration. So
indeed,
all very appreciative.
Very good. Very international too. I like that. Very good.
Yeah. Very
cool. Okay.
Okay. Well, some quick background first. We have this paper is about a very special long duration gamma ray burst, and long GRBs occur at the end of a star's lifetime as it collapses into a black hole, and then it releases a highly collimated jet of material, and that ejecta interacts with the circumburst material, and it emits an afterglow in the X-ray and radio X-ray through radio wavelengths that then fades over time, and that we can observe over, as far as a few months, as we've seen with this one.
Yes.
We also know that high luminosity long GRBs occur less frequently overall, so we observe them less in the nearby universe. So in this paper, we investigated a very energetic long GRB that was also very nearby in GRB terms. That was called GRB 221009A, that people often refer to as the brightest of all time, or the boat.
The boat. I like the boat. Let's call it the boat. Okay.
Yeah. So on October 9th, 2022, Swift's burst alert telescope triggered twice on a bright new transient. So it triggered and then it automatically slewed to point at the source, and then it triggered again, which is kind of unusual.
Yes.
So based on that and the type of trigger and the location of the source, which was just a few degrees away from the galactic plane, we didn't think this was a GRB at first. We thought it was a galactic transient.
Okay.
So we reported it. And then we soon found out that the Fermi Gamma Ray Burst Monitor also triggered on a GRB about 55 minutes before.
Ooh.
And that the location of this Fermi trigger was consistent with the BAT trigger. So we'd also analyzed the X-ray data a little bit more at that point, and we came to the conclusion that these triggers were the same, and that the BAT transient that we saw was actually the afterglow of the GRB that Fermi had detected, which was GRB 221009A.
Wow.
And this is pretty cool because BAT has never triggered on the afterglow of a GRB until now.
Very cool. Very cool.
Yeah. So since this was a very unique burst, it got a lot of follow-up and observations from different facilities, including the MAXI and NICER observations that we included with the SWIFT data set. And a lot of these observations confirmed that it was a extraordinarily bright burst. It even was detected by radio transmitters as a sudden ionospheric disturbance. And we got spectroscopic observations of the afterglow in the host galaxy that confirmed a redshift of 0.151, which is relatively close as far as GRBs go. There's only about 12 Swift GRBs with redshifts that are closer. So we show in the paper later that this combination of high luminosity and nearness make it the brightest of all time. We also compare it to the other Swift GRBs that we've seen, and we estimate how often we can expect an energetic event like this to occur within that distance.
Awesome. Awesome. Very cool. Okay.
All right. Simone, do you want to talk about the observations and the data reduction now?
Absolutely. Yes. Yes. Thanks, Maya. It was a very nice introduction. And in the next part, I want to walk the reader through the data reduction and analysis section, starting with the detection of the GRB by the burst alert telescope on board of SWIFT. If we go to the figure 1, we can see here the zero time, and the top panel is the raw light curve as detected by the BAT detector. So raw means not background subtracted. 0 here, the time 0 refer to the Fermi GBM trigger.
Okay.
You can see that the green time interval is the time interval when this source was occulted by the Earth for SWIFT. So it wasn't possible during that time to observe the source. You see also there is an interval when BAT was disabled because it was crossing the South Atlantic anomaly. You can also see the increase of the count rate immediately before and the decrease immediately after. After we exit the South Atlantic anomaly, the gray intervals are intervals when the satellite slew on source position, on position of sources that are in the plan. So all these sources are planned to be observed with SWIFT. So immediately after the South Atlantic anomaly, we slew on the first planned source. And you see the increase in the count rate there. It means that the source entered in the field of view. The point is, immediately after this slew, we notice a smooth decline of the flux. That smooth decline is already the flux coming from the GRB. Although the GRB wasn't inside the field of view at that time, you can see in the bottom panel the coding fraction, so the part of the codec mask of BAT that was illuminated by the GRB. And you can, 0 means that the GRB was out of the codec mask, So at this time, 2,500 seconds, with about 40 minutes after the original GBM trigger, you see that the source was not inside the codec mask.
Right.
Although we noticed the flux increase, but we didn't trigger because of that. After 3,200 seconds, more or less, there, we slew to another source. And at that point, the GRB entered in the codec mask. You see that the coding fraction there is around 0.2.
Mm-hmm.
And at that point, we had the first trigger on the GRB.
Mm-hmm.
And at that point, automatically the satellite, every time we detect the GRB, slew on the position of the GRB. You see that there is a slew immediately after the trigger there.
Yeah.
And the source enter completely in the coded field of view. And the interesting thing about this GRB is also that it triggered twice, but indeed after 3,600 seconds, it triggered again.
Wow.
And so taking this into account, and also taking into account the fact that the flux was decreasing in a very smooth, linear way as a power law, basically, as expected for the afterglow of GRB. As Maia mentioned, we realized that what we were seeing was not the prompt emission of the GRB, but was the afterglow. And as Maia mentioned, it's the first time in more than 18 years of Swift operation that BAT trigger on an afterglow of GRB. That's pretty remarkable by itself. Yes. So at this point, the satellite was pointing at the GRB because it's loose, and observation with the other instruments on board of Swift started. So we started observing with the X-ray telescope, XRT, on board of Swift about 170 seconds after the BAT trigger.
Okay.
And if you go down to figure 2,
Swift.
Figure 2, yeah.
Yeah.
That's one. So we realized immediately that we were observing a very bright source. I mean, the flux at the beginning of the observation was pretty high, and it was like 900 counts per second, which is 10 to the minus 7 erg per centimeter square per second.
Yeah.
And that's more than an order of magnitude brighter than any other observed GRB. We will see that later when we do a comparison with the other GRB observed by Swift. XRT observations switched between different modes depending on the flux. So when the flux is higher, it observed in the one-dimensional window timing mode, and when the flux decrease below a given level, we transition from the WT mode, the window timing mode, to the PC mode. And here the points, you can see the point in blue are in WT mode, and the orange one are in PC mode, photon counting mode. Now, the difference between the WT mode and the photon counting mode is that the WT mode has a very fine, refined time resolution of 1.8 millisecond, but you cannot construct an image because it's one-dimensional. Right. The PC mode on the other side is two-dimensional, so you can do imaging. We can see here in this figure also the flux measured by the other detector that Maia mentioned at the beginning. So the MAXI detector and NICER. You can see that MAXI started observation actually before the BAT trigger, around 2,500 seconds, which is about 41 minutes after the Fermi trigger. Although this early detection was not promptly communicated to the ground due to a loss of signal.
Oh.
So it was reported later.
Okay.
Then nicer, you can see also nicer observation there. They are in the red one. They started about 3.9 hours after the trigger, and they continued up to 42 days after the trigger.
Oh, wow. Okay.
Now, one interesting thing here about the X-ray analysis is that we immediately realized from the WT mode image profile that there was a clear excess compared to the one expected from a point spread function. If you go, this is discussed in detail in the appendix, but if you can go to figure 8 of the appendix.
Sure.
Because in that figure, okay, let me see, figure 8.
8, there we go.
That's the figure. I mean, you can see here the dashed line is the point spread function profile, PDF profile,
Okay.
PSF, and you can see clearly in the wings that there is an excess in the size.
Right.
When we transition from the one-dimensional, so from the WT mode to the PC mode to the images, we realized that this was due to dust rings, and that's clear in figure 3. Actually, if you go back to figure 3, you can see the PC mode images.
Yes, figure 3. Let's take a look at those images. There we go. There's the PC mode images.
Right.
Wow.
And so, yeah, you can clearly see the dust rings here.
Indeed.
Wow. So we use this on one side. These complicate the analysis of the light curve and spectra of the source, because the background is not a standard background, but is different than a standard background. So you need to use a tailored approach in order to remove the background.
Okay. And
the details about this treatment are discussed in the text, in the appendix. The point is that, fortunately, the impact of this is only marginal in the flux estimation, the light curve. It's also, I mean, the flux is accurate at 6%, so it's only a marginal effect.
Okay.
Although it's more relevant, the impact is more relevant in the WT spectra, but it's not that big anyway. On the other side, the dust scattering rings provide very important information about the distribution of the dust in our galaxy. Indeed. And this is something that Maia will discuss later, so I'm not discussing this right now. So in table 3, we can see, if we go to table 3, is below.
Yeah, sorry. Table 1,
sorry, table 1, sorry.
Table 1. Okay.
Yeah, sorry.
It's all good. It's all good. Let me go back. Table 1. Yep, these are the parameters derived. Okay, here we go.
This is the time resolved, the results of the time resolved spectral analysis in X-rays, as conducted by with the XRT, NICER, and MAXI data. So you can notice here that the photon index measured by MAXI is in general a bit higher than the one measured by XRT at similar times. This is likely due to the contribution of the dust rings, so that are not well subtracted in the background subtraction. I mean, because MAXI cannot spatially resolve the rings, so it's more complicated, the background subtraction in this case. But mitigation of this effect with MAXI and NICER data is discussed in the text in the appendix. I'm not going into detail for this. But yeah, so these are the result of the time-resolved spectral analysis, which are important for further discussion later. And Maia is going to discuss about this in the broadband SED analysis later.
Okay.
The result of the optical and UV data reduction are also shown in figure 2. If you go back to figure 2,
Yep.
you can see the
I got both up.
the bottom one is the UVOT light curve with the different filters. So with the optical filters, UV filter, and the white filter. Here, a note is an important note about the analysis is that it was basically complicated by the fact that there is a nearby star. So we had to use some template images taken later times, like 49, 50 days after the GRB, and use them in order to subtract the background contamination and find a refined photometry for these light curves. But these light curves are already refined. And that's pretty much all about the analysis. So at this point, I think I'm passing the ball back to Maia, that is going to discuss the result of the analysis the following discussion. Go ahead, Maia, if you want.
Yeah, okay. We can stay on this figure and talk about the light curve real quick. So for the X-ray flux on the top panel, we have the XRT window timing and photon counting modes, as Simone mentioned, and the MAXI and NICER data have been extrapolated to 0.3 to 10 keV to better compare with XRT.
Okay.
And for this X-ray light curve, we don't observe typical afterglow features like a prompt decay phase or a plateau phase or any flaring. And we found that it was best fit with a broken power law model with a break at around T0 plus 79 kiloseconds.
Okay.
And then for the UV light curve down below, we found that a single power law and a broken power law model both, had comparable fits to the data, but in either case, the UV light curve decays slower than the X-ray light curve. And since there is high foreground extinction due to this being so close to the galactic plane, we believe that is the accurate behavior of the afterglow, and that's not caused by an emerging supernova or by the underlying host galaxy.
Okay, got it.
So if you scroll down to figure 4.
Figure 4. Let's go to figure 4 is analysis equation 1 on dust. Figure 4, dust. We're going to talk dust.
Yeah. So we also analyzed that very pretty dust scattering echo that complicated some of the X-ray analysis, but it allowed us to investigate the dust in our galaxy along the line of sight to the gamma ray burst. Because as light travels from the source, the photons that weren't traveling in our direction are scattered by dust clouds, and they get scattered into our line of sight. So the smaller rings are formed by the more distant clouds, and then the larger rings are by clouds that are closer to us. Okay. So in equation 1, sorry to detour for a little bit.
It's okay. It's all good. Equation 1.
But we can use this equation to determine the distances to the dust clouds, because we can approximate, since the distance to the GRB is effectively infinite compared to the distance to the dust, which is in our own galaxy.
Oh, yeah. Okay.
So for figure 4, we have the dust column density histogram for an MRN model, and we use the Fermi GBM data to assume a soft X-ray fluence, since we didn't have observations of the prompt emission. And we also found that the largest concentrations of dust were located at 200 parsecs. Oh yeah, you can go back up to figure 4 with the histogram. So we see large concentrations of dust at 200 parsecs, between 400 and 600 parsecs, and at 700 parsecs, we're along the line of sight to the GRB, where we would expect them to be within our galaxy. But we also found evidence for a smaller dust cloud beyond 10 kiloparsecs, which would be located above the galactic disk, where we don't expect to see very large concentrations of dust. So this technique is cool because it allows us to see very small concentrations of dust at very large distances that we might not be able to see with other techniques.
Right. Cool. Very cool.
Okay. We could go to figure 5 and table 2. They're right next to each other.
All righty, let's get there. Figure 5 and table 2.
Oh, and this shows the fits for our broadband spectral energy distributions. Since we saw some spectral evolution in the early X-ray afterglow from the XRT window timing data, and also saw some in larger time scale from the PC mode data, and we saw that these were consistent with the Maxi and Nicer spectra. So we created 2 spectral energy distributions at T0 plus 4.2 kiloseconds and at T0 plus 43 kiloseconds using the BAT, XRT, and UVOT data. And then we also, for each epoch, we also created fits with just BAT and UVOT, because as Simone mentioned, the XRT window timing data is affected by the dust scattering echo.
I'm with you.
So, so overall, we found that a broken power law model is preferred for both of the models, with a photon index of about 1.7 and a break energy in the X-ray bandpass, and some host galaxy reddening between 1.3 and between 0.3 and 0.5 magnitudes. Okay. And an NH between 1.1 and 1.4 times 10 to the 22nd.
Okay. Yes.
But we mentioned that this precision is limited by the dust scattering echo and its effects on the spectra. And we also go into more detail in one of the appendices about how we built the SEDs.
Nice. Very cool. Very good.
All right. I think the next figure is the comparison plots for XRT. Do you want to talk about those, Simone?
Comparison. Previous GRBs. Yes, there we go. Comparisons. There we go. I'll blow this up a little bit. Okay.
Yes, I mean, the most interesting part here, I mentioned a bit this before. I mean, you can see the X-ray light curve in flux and on top, the top panel. And you can notice immediately that it's above any other GRB observed before. And I was mentioning about, I was talking about the first observation before, so at the very beginning of that light curve. But you can notice even a later time that, I mean, the flux is more than an order of magnitude. It's about an order of magnitude higher than any other GRB observed before. That we are showing like some pretty luminous GRBs, energetic GRBs observed before in the past, 1304 27A, which was for the most the brightest GRB before 2210 or 9A, and another pretty bright GRB was 08 or 319B. Yes, the naked eye burst.
What is NGRB? What is the color scale?
The number, how many GRB
number. Okay.
Yeah.
I'm with you.
In the bottom panel, that's the other interesting thing is that although this flux is the highest ever measured, in terms of luminosity, this GRB it's in the higher part of distribution. So the luminosity is pretty high, you can see compared with the population, but still is not the most, is not the highest luminosity ever detected. So I mean, this is part of what will be discussed later probably, but it's the point is that this GRB it's particularly special because it was energetic, not the most energetic, but quite energetic, and it was nearby. The fact that it was nearby is what really make it the brightest of all time. The boat, as people call it, that's the main things that I wanted to stress on the comparison with the other GRBs.
Okay.
After that,
How
Oh
often?
yeah, you can go ahead. Yeah, go ahead, Maya.
How often are we going to
Okay.
see one of these?
That's
Uh,
the
yeah, that's the question.
That's an interesting
Um,
question.
So we try to estimate the rate that we can, see future events like this.
Mhm.
And because Swift was Earth occulted during the prompt emission, we use the Fermi GBM light curve and spectrum to derive affluence for the main pulse of the prompt emission,
Okay.
just between 218 to about 280 seconds after
Yeah.
T0.
Okay.
So we tried to derive affluence in the BAT bandpass 15 to 150 keV to better compare with the previous Swift GRBs. So we found that the BAT fluence would be 1.86 times 10 to the negative 2 ergs per centimeter squared, which
Okay.
is 50 times higher than the largest fluence detected by BAT, which came from GRB 130427A.
Cool.
And we also derived an isotropic energy in 15 to 150 keV at redshift 0.151 of 9 times 10 to the 53 ergs. So we use this information to estimate the relative rate of a similar event. We use the intrinsic long GRB luminosity distribution and rate to randomly generate 10,000 long GRBs. And we assigned each long GRB a real pulse structure from the BAT sample and calculated the isotropic energy for each simulated burst.
I'm with you. Mhm.
Okay. And of these 10,000 simulated long GRBs, only one of them had an isotropic energy that was higher than GRB 221009A.
Okay.
So we conclude that only about 1 out of 10 to the 4 long GRBs are as energetic as GRB 221009A.
That means.
And then we use that value in equation 3 right there to estimate that BAT should have detected about 1 GRB like this in about its lifetime, or in 17 years, independent of distance. But since this is also one of the closest Swift GRBs, we estimated the intrinsic rates of a similar event like at the distance that GRB 221009A is at.
Okay.
And we use the BAT trigger simulator to do this. And the BAT trigger simulator uses a combination of instrumental setups, such as the number of enabled detectors and the part of the field of view that the GRB is detected on, to calculate the highest possible redshift that BAT would be able to detect the GRB.
Yeah.
So we set the upper limit of the detections to be 1 per 18 years, because BAT didn't even detect this one during the prompt emission. It saw it afterwards.
Yeah.
And then we derive an upper limit on the flat intrinsic co-moving rate to be 1.6 times 10 to the negative 4 per gigaparsecs cubed per year. And then we use that upper limit to find the upper limit on the all sky rate of similar events, which would be 1 per, 1 out of 0.05 years.
Right.
And then, so yeah, the appendix goes into a lot more detail. But then finally, we get the rate of events as energetic as GRB 221009A to be less or equal to 1 times 10 to the negative 4.
Okay.
And then, so within the volume of just redshift 0.151, we find that we would need to weight the rate of events as energetic and nearby as GRB 221009A is just less than 1 per 1,000 years, actually. So we'd have to wait quite a long time to see another one.
Or we get lucky.
Yeah, maybe.
Serendipity calls.
Yeah.
Very cool. Very nice. Lovely, lovely. Oh, and I should mention that, this is there's a whole focus issue on this GRB. And so if you're interested in a lot more information about this GRB, do check out the total volume there on GRB, or just the boat. We'll just call it the boat. Very cool. Very cool. Here we go. All righty. Maia and Simone, I want to thank you so much for walking us through your very lovely APJ letter. Thanks.
Thank you.
And so we kind of hinted at it a little bit there toward the end of 1 out of every 1,000. And so let me push on that a little bit. And where do you think we go with this over, let's say, timescales of the next 2 to 5 years? Are there additional multi-wavelength observations could be particularly brought in on this one? Is there additional theoretical modeling that could be done? Additional dust modeling that could be done or needs to be done? Yeah, and just sort of where do we go from here, given the boat?
Probably all of that. I know that Swift is still observing it for as long as we can. I imagine that there will probably be a lot of interest from other facilities that can still observe it. What do you think, Simone?
Well, there is also the fact that the multi-wavelet, so all the emission that we saw in a different wavelet in X-rays, optical, for the afterglow, it cannot be, I mean, this emission cannot be described by a standard top part model. The standard fireball top part model used to describe the GRB. I mean, it doesn't seem to be consistent with this close relation. So there is something not standard that is going on with this GRB and need to be investigated. And actually, there are several work that are trying to investigate this. And we discussed this a bit also in our paper, but only Swift observation doesn't allow to draw a firm conclusion on that. On the other side, I wanted to mention that, I mean, all nearby GRBs are important in general. I mean, this one was clear. It was very energetic and nearby, so it allowed that once in a lifetime occasion to study a GRB with this level of details, you know. But all the other nearby GRBs are important and provide important features, an important occasion to study GRB. So in the near future, I would expect more nearby GRBs that could be useful in order to investigate this kind of phenomena.
Yeah, cool. Okay, very nice, very cool. Maia, Simone, I want to thank you so much once again for walking us through your awesome article. Congratulations.
Thank you very much to you.
Congratulations on that one. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.